Hello, this is Sid, and I will be presenting on the choice of the shuttle vehicle and the architecture of our perception sensors. The vehicle we chose was a 2018 Ford Transit Connect. We chose this vehicle because we found that this vehicle was large enough to transport both people and luggage for about 7 passengers, and the vehicle is small enough so that it can easily maneuver through a population-dense area such as Easton. Here's a slide that shows all the specifications for the vehicle. The vehicle has a wheelbase of just over 3 meters and weighs around 2,360 kilograms. The vehicle itself weighs 1,800 kilograms, and then we approximated around 80 kilograms per passenger and their luggage. Now, most of this information was sourced through either the Ford website or auto magazines such as Car and Driver, and also some parameters from the National Highway and Transport Safety Administration, or also known as NHTSA. The references for all of these parameters are provided towards the end. However, a few parameters such as the inertia of the wheel, the longitudinal and the cornering stiffness of the tire was estimated from the previous homework because we were not able to get accurate tire data. Now, we believe that if these tires are tested and we get accurate tire data, our simulation will be much more representative of what the vehicle would actually do in this scenario. Here's a picture that shows the vehicle overlaid with all the perception sensors. We have a LiDAR right at the very top. We also have a forward-looking camera that's placed inside the vehicle. We also have a medium and long-range radar. We also have short-range radars on the side and on the front and on the rear. And these radar are extremely important, because especially in a place like Easton, because they will give the information to the vehicle to say if there are any bicyclists or any pedestrians that are coming in from any direction towards the vehicle. And that can be used by the vehicle to determine if it needs to stop or if it needs to go. We also have a GPS unit that is integrated with the IMU to give accurate roll, pitch, and yaw information. We also have a wheel speed sensor that gives accurate speeds of each wheel, and all of this information is then processed by the computer control center inside the vehicle. Here's a picture that shows the superimposed fields of view. Our LiDAR, which has a very high resolution, it has a 190-degree field of view, and it's available in 3 planes with a radius of 50 meters. We also have a forward-looking camera with a field of view of about 60 degrees with a 90-meter range. We also have a long-range radar with 175 meters of range with a 10-degree field of view, whereas our medium-range radar has a 60-meter range with a 45-degree field of view. Now, we did talk about the the short-range radars on the side, and here's how they will be placed. And these short-range collision-detecting radars have a range of about 4 meters, and as the name implies, they're primarily used for collision detection. This slide shows the description of each sensor. And so the LiDAR is a forecast 3D sensor, and it's used to create highly accurate 3D maps of immediate vicinity. We also have a radar, which is used for adaptive cruise control and emergency braking assistance. And the short-range radars are used for collision alerts, blind spot alerts, and side collision alerts. And both the radars are manufactured by Delphi. And we have a camera from Mobileye, and this is primarily used for forward collision warning, pedestrian and obstacle, and vehicle identification. We have our integrated IMU and GPS unit, and the IMU is a 6-axis acceleration and angular rate unit with integrated GPS module with real-time kinematics. And the GPS antenna that we chose can communicate not only with GPS, but also with GLONASS, Galileo, and Compass satellites. And this will determine highly accurate position of the vehicle to within 3 millimeters. And our wheel speed sensor is made by Kistler. It is protected by IP67, which means that it is protected under extreme conditions such as mud, snow, water, and rocks. And so our wheel speed sensor is quite durable, and that is used for accurate measurement of wheel speed, which will then be used to determine vehicle speed. Now, here's a layout of our communication diagram. All of our sensors communicate via CAN, and we decided to design these sensors across four different CAN buses. And if you notice, we have a high priority, and then we also have a lower priority. The reason being, the data coming from LiDAR, the medium range, wheel speed, and GPS, a lot of these sensors are used for obstacle detections and obstacle avoidance. And those sensors need to have highest priority when they come into the control module. If we only had one CAN module, or one canvas, then only one of those messages would have the highest priority. Every other message would have a low priority, and they would come after the original message came through. In some instances, that may be too late for the computer to make the decision. So we decided to split the sensors across four different CAN buses, so you could have four different sensors having the highest priority. So the sensors with the highest priority will come to the controller unit at the same time, and then you have the lower priority sensors such as the IMU, short range camera, and the long range radar. And all of these are then integrated into your data acquisition system, and the sensors are then fused. So the next slide shows a block diagram showing the interconnection. We have the sensors with the LiDAR, the radar, the camera, GPS, IMU, wheel speed, and the short range radar, all integrated into the processing unit, which is our computer, which then communicates to the execution part of the vehicle, and it gives the command to the control system, such as the brake, throttle, and steering system. And then that information then goes to the vehicle user interface, and that will give the user inside the speed, the distance to a journey, and any alerts about if anything's going on around in the immediate vicinity. And now I'll pass it on to my teammates. Thank you very much.
Starting out with the technical challenges, we will have the low-level longitudinal control. To create the longitudinal model, most of it was taken from the longitudinal model of Homework 2, with the parameters being updated for those of the shuttle. However, there are certain features of Easton Town Center and Columbus as a whole that means that the model did need to be adjusted. Now, one example of this is how the path at Easton Town Center is all flat, so the alpha value will always be 0 and does not need to be accounted for. Another factor is that Columbus is a city that deals with wind regularly, and so it's necessary to model how wind will affect the shuttle in its daily operation. Examining the equations, first we have the longitudinal dynamics equation. For simplicity, the equivalent mass is treated as 0.1 of the normal mass, which gives a rotating mass factor of 1.1. And with alpha being equal to 0, a grade force can be disregarded. Both of these very much so simplify the equations. For the wheel dynamics equations, you have the wheel moment balance equation, the longitudinal force equation, which is a function of S, and then you have the equation for how to calculate S in the far right. Also needed is the simple model equation, which was given as part of homework 2. In the wheel dynamics equations of the previous slide, and you can also see the fx MATLAB function. The S subsystem takes the velocity and omega r omega and calculates the S, and then the tire mod function takes that S and calculates the force. Now the first graph shows the shuttle accelerating up to its steady state value, which is about 6.7 meters per second, which is the equivalent of around 15 miles per hour, which is the speed limit of Easton. And this graph shows how the shuttle can steadily accelerate up to its steady state value and can cruise along at the speed limit of Easton. And this shows that the shuttle will in fact comply with Easton's speed limit. This graph shows the shuttle braking to a stop from its steady state velocity. This graph shows that the shuttle is capable of departing from one station, cruising along at the speed limit of Easton, and then coming to a stop at the next station. This third example shows the shuttle encountering wind resistance, and this graph shows just how much of an effect even 3 Newton meters of wind can have on the overall velocity of the shuttle. And Columbus being a city that has a number of windy days, it just shows how important it is for this to be taken into account of when the shuttle is being modeled.
Hello, my name is Lynn and I'm going to talk about the low-level lateral control. So before implementing this, we have to check that the vehicle is understeer. For that reason, we're going to use the understeer formula here and the yaw velocity gain. Using the cornering stiffness provided for a shuttle vehicle, we find that the understeer gradient is positive. Since it's positive, we can say that indeed our vehicle is understeer. And we can see the plot of the yaw velocity gain versus the vehicle speed here to the left. We can see that the maximum yaw velocity gain is attained at around 90 meters per second. And it decreases afterwards. This understeer characteristic is enough for our vehicle since our vehicle is going to operate at low speed, around 5 meters per second or 18 kilometers. So to decide the linear and the non-linear lateral models, both were implemented and their outputs were compared. A PID controller was added to the speed error to prevent it from going to zero. It was calibrating to have a settling time of around 2 seconds. And a yaw moment disturbance input was added between the steering angle projection block and the vehicle dynamic projection block, here and here. The outputs, we obtained the results for values of velocity of 2, 5, and 10 meters per second here. So here we have the results. Here we have the results that we got with the different velocities. We have the velocity of 2, 5, and 10 meters per second. In the three plots that we obtain, it's clear how close the linear and the nonlinear models react when the shuttle is set to go at low speed, up to 5 meters per second, so in the first and in the second cases. The responses of the yaw rate are underdamped. Here we can see that they're actually underdamped for the nonlinear model, but the settling time is less than 1 second in every case, which is a good characteristic of the model. However, some discrepancies between the models appear when the speed is higher than 10 meters per second, as we can see here in the slip angle of this result. Thus, the linear model can, however, since the vehicle will be set to operate at low speed, around 5 meters per second, both the linear and the nonlinear model satisfy the requirements. Thus, the linear model can be used for the path following task. Now let's talk about the path planning and following. For the path following, we use a linear low-level lateral control and expand the state space to include the yaw angle relative to the desired path's tangent, and here the lateral deviation from the desired path at the preview distance. We also reduce the number of inputs, eliminating the input to the rear wheel and the yaw moment disturbance, as we saw previously that didn't affect greatly the performance of the model. So we will just have as the input the steering angle applied to the front wheel, delta F, and the road curvature, rho ref. This road curvature will have a saturator to avoid exceeding the steering limitations of the vehicle. To generate the path, in first place, the latitudinal and longitudinal coordinates of every corner of the path were obtained using the website lotlong.net. After that, we translated these coordinates to XY coordinates using this command in MATLAB. And then to facilitate the computation, we perform a change of coordinates to have the starting point of the path as 0, 0, and this is the starting point of the path. To facilitate the path generation, all the long paths were approximated to be straight lines, and the corners were smoothed using circular arcs of radius 3, and a function interpolated in MATLAB. The path joining the closed loops was generated here using these three control points and a third-order spline in MATLAB. We can check that the path is indeed smooth, as shown by the plot of the road curvature derivative. Here, where the derivatives belong always to the range -2 to 2, so the path is guaranteed to not have big discontinuities. We have to comment that for this project the path was generated in almost a manual way since the path has been divided in several segments that were treated differently. However, in general, the path should be generated taking into consideration not only the control points that are the corners, but also following corridor constraints, since the shuttle is supposed to be operated in an environment where it has to follow a straight line precisely and not bump within its lane. From these references right here, we can summarize that the path generation should include corridor constraints and is more effectively solved when it's formulated as an optimization problem, where also speed constraints of the vehicle and the lane can be taken into consideration. And here we have the block diagram used for the path following. Aside from the smooth path, the value of the road curvature rho ref has to be saturated. So here we have the upper limits and the lower limit that were used. That's 17 degrees for steering in both to the right and to the left. As explained before, we're going to consider that the vehicle has a constant velocity of 5 meters per second, and it will be using a preview distance of 2 meters. Also, we had to recalibrate the PID used here. Since the vehicle is different and its parameters are different, the PID had to be calibrated again. So these are the parameters that we got for the PID to have a bandwidth of 16 radians per second and a phase margin of 70 degrees. And this is the result of the path following. The starting point of the shuttle is a point 0, 0 as explained before. From here, the shuttle goes to the right and follows the whole path. The smooth path allows the following to be performed with almost no error during the first 700 meters until reaching the spline, where the accumulated error starts becoming more noticeable. Even though the vehicle never goes out of track, it's clear that by the end of the circuit there's a path accumulated error of around 5 meters, which could be corrected using a different controller for the lateral deviation from the desired path at the preview distance. Analyze the path following results. At the point of the discontinuities in the derivative graph to the right, we have the discontinuities of the other parameters that are here to the left. When the parameters here change from positive to negative or vice versa, the vehicle performs a sharp action, such as steering left or right, which is needed for the vehicle to make turns. The values within those changes are limited by the saturator, which allows the vehicle to follow the trajectory relatively smoothly. Here we can also see that the path following error has in average a really low error. So here we cannot notice how big the error in the path following is. However, we can notice that when we get a plot of path error versus time. So here it's also clear how the discontinuities in the derivative graph provoke discontinuities in the path error, while the x and y errors remain relatively small from the initial portion of the path. They are accumulative and start increasing towards the middle end of the path. This implies that a more robust controller will be needed here to allow the vehicle to return to the path and overcome the accumulated error.
Now we'll be talking about collision avoidance for the shuttle. For collision avoidance, the challenge is not only making sure that the shuttle is capable of avoiding a crash, but it's also making sure that the methods used consider social acceptance factors, such as respecting personal space of human drivers, their cars, and of pedestrians on the road. Since there's only one lane of traffic in each direction at Easton, the methods described in Unit 7 of collision avoidance of swerving around possible crashes is not applicable. Instead, the group decided to use the method of stopping before a collision event and waiting for it to resolve itself. This has modeled using the ABES implementation done in Homework 5, and this is the basis for the group's collision avoidance model. Some changes from the Homework 5 model include eliminating the lead car as it is unnecessary. And so the lead car is said to have a faster velocity than the speed limit, so that the group shuttle will never get near enough to the lead car for it to interfere. The obstacle item in this case will be a pedestrian, and so the velocity of that pedestrian will be 0 meters per second, forcing the shuttle to come to an immediate stop. The state flow from homework 5 will be the same, however the speed limit input will have to be updated to 15 miles per hour, which is approximately 6.7 meters per second. Then inside the equal car block, the transfer function will be updated to the one calculated for the group shuttle in the longitudinal model. Shown now is the state flow from homework 5 that the group used to model collision avoidance. This shows how if there is no object detected, the shuttle will move along at the speed limit. However, if an object is detected, if it's far away, then the shuttle will go at the same velocity as the object. However, if it's close enough, then the shuttle will immediately come to a stop. This here shows the updated Simulink model from homework 5, and it shows the decision-making chart as well as the detection for the object, the obstacle information, as well as the ego cars information. This graph shows the shuttle accelerating from a stop to its steady state value with the speed limit, and then at 70 seconds it encounters a possible collision event, which in this case is a pedestrian, and it comes to an immediate stop.
Hey guys, I'm Kevin, and I'll be talking about localization and perception, particularly in the case of cars and pedestrians for our autonomous shuttle. So when we say localization and perception, we basically mean the autonomous shuttle's ability to detect obstacles as well as position the obstacles with respect to its own position. And so there are many ways you can do this, but MATLAB's automated system toolbox offers a variety of tools which can already be used particularly for this purpose. So we'll be looking at the different stages of perception before focusing on the algorithm specifically used. So the first stage of perception is visualizing data. Now, because autonomous vehicles have a variety of different sensors with different sampling rates and data formats, in order to understand an idea of how much the environment is covered by our sensors, we use what is called a bird's eye plot, which gives you an idea of information regarding the area covered by our sensors, the objects detected, and overlays our lane detection from our previous part into our images. The second part is automatic ground truth labeling. And ground truth is basically a machine learning term which refers to the measurement of the variables we use and is basically the process of taking in the initial video frames and labeling objects in them. And this process is actually quite cumbersome because the software can't recognize objects immediately, and you will need to actually specify pixel by pixel of what an object actually is. But MATLAB's automated ground truth labeling processor does this automatically, and it does this because of its four main key features. One is its vehicle detector, which automates the detection and labeling of vehicles in keyframes by using an aggregate channel feature. The second one is the temporal interpolator, which basically detects specific objects across all the keyframes. These would generally include like the road as well as the lanes. And the third one is the point tracker, which uses a version of the KLT algorithm to track regions of interest across frames. The KLT algorithm is basically a tracking algorithm in image processing, which is used to detect it uses the sum of the squared differences in the intensities of pixels across a window of interest in all of keyframes, and it basically tracks this window in real time. And the fourth feature is an add algorithm feature, which lets you add your own custom algorithm, which can help facilitate the whole process. And as you can see in the image shown of the automatic ground truth labeling in action, so once we loaded the keyframe, and we run the tool, it automatically detects known obstacles as well as as well as things like the lane guidelines, and the road as well. And so you can see in the image that the cars have already been labeled, as well as the lane has been detected automatically and labeled accordingly. The third part is sensor fusion. Now, as I've said, the autonomous shuttle has a variety of different sensors with different sampling rates. And not only that, they actually give you different outputs for the same object. For example, shown in the image below, you can see a car, in which the case our perception systems using vision and using radar actually give you different values for the same car. And so what sensor fusion does is that it takes an average of these values and gives you an estimate of where the car's actual position is, and that's shown by the circle represented in the image. So now that we talked about the different stages, we'll go into how perception is done using vision systems and radar systems. So I'll first talk about vision systems. So the way we use perception using vision systems is that there are basically two major parts of perception using vision system. One is pedestrian detection, and another one is vehicle detection. So pedestrian detection uses aggregate channel features to detect pedestrians. And when we say aggregate channel features, we basically mean it measures pixel intensities across different channels, where channels actually refer to, well, in the case of an RGB image, it would refer to the individual colors, so red, green, blue. And based on that, it tries to detect and uses, based on the differences in intensities, it detects a particular pedestrian. And vehicle detection is done using regional convolutional neural networks, which basically is an algorithm that divides an image into different boxes or regions and tries to fit and tries to see if an obstacle lies within a particular box. If it doesn't, it just reshapes the boxes such that it can actually detect obstacles eventually in the image. And the main steps for implementing the process of perception are given below. So first you need to define your camera intrinsics and mounting position. The camera intrinsics would refer to your camera aperture, your frame rate, and the mounting position is basically where you placed your camera, which in our case is in the front of the vehicle. Once you've done that, you need to load and configure the pre-trained vehicle detectors and the pedestrian detectors, which basically use the ACF and RCNN algorithms. And you also need to set up the multiple object tracker, which basically uses the pre-trained vehicle detectors and pedestrian detectors to track multiple objects at the same time. And once you run the multiple object tracker for initial video frames, or which we refer to as the training process, you'll automatically upload the tracker with the detection results and display it over the video in real time. The second part is perception using LiDAR. In addition to vision system, the LiDAR system can also be employed for perception and localization. Each LiDAR scan stores data as a 3D point cloud. To efficiently process such data, fast indexing and search capabilities are required. And this is generally achieved by using a KD tree structure. A KD tree is basically a binary tree in which every leaf node represents one of k different dimensions, and the tree itself divides space into different hyperplanes. And it's basically more of a data structures thing, so I won't focus too much on it. And the ground plane fitting is done using the ransack algorithm. The ransack algorithm is a random sample consensus algorithm that basically is a method of line fitting. And what it does is that instead of conventional line fitting, the algorithm efficiently removes outliers from your data set so that it gets the smooth line which you would generally need instead of one with spikes because of certain random data that comes into sampling. So the steps involved for setting up your perception system using LiDAR are: first, you select a point cloud region for display. So this is basically a region of interest where you want to collect LiDAR data from. And this would generally, in our case, be about 20 meters to the left and right of the vehicle and about 40 meters front and back. And you load data from this point sequence cloud. And once you've done that, you need to segment the different parts of your data. So the first thing you would need to do is segment the ground plane and the obstacles. And this is done by, again, ransack algorithm. So what ransack does is that it finds by the ground plane, which would be the inliers of our data, and any obstacles would be potential outliers. So by using the ransack algorithm, we'll be able to extract both the ground plane as well as our obstacles. And we generally set this to be about 10 meters in radius from our shuttle vehicle. And the third part is to segment the ego vehicle. So because your LiDAR scan is mounted on your vehicle, the vehicle itself would be detected in your LiDAR data. So you would also need to train the LiDAR to ignore this data. So what we do is that we use an axis-aligned bounding cube to represent the ego vehicle, and we generally train the algorithm to ignore this particular region, as it generally just slows down our computation speed. So once you've done this, the final part is just processing the cloud point sequence. And once the player is configured, you just run it in real time and it'll slowly start processing data, and you will also be able to see it in real time. So what you see here are two different images. The first image represents the initial LiDAR scan, and the LiDAR scan, so here we can't really make sense of any of this image because this is just random information. And the second information shows you after we've segmented our data. So the green lines represent our ground truth labeling, and the red represents the obstacles detected. And if you can see, the white region in the center represents our ego vehicle we've chosen to ignore. And the blue points are basically outliers from our LiDAR scan and are basically of no interest to us at this point. So once we have perception done, we need to localize our obstacles as well as our data with respect to our vehicle. So what we use is that MATLAB's robotic systems toolbox actually does this really well with the help of the Monte Carlo localization system object. So the object basically uses the MCL algorithm and the Monte Carlo algorithm to estimate the vehicle position using the GPS, IMU, LiDAR scan, and sensor data. And it does this by using particle filters. So a particle filter is basically a dispersion of different particles where every particle represents a possible state of the vehicle. And eventually, as we gather more and more data from our sensors, the particles begin to converge to a single point, and this helps to track the vehicle motion. And so the process of the MCL algorithm basically involves three steps. And the first one is like the particles are propagated based on change in pose and the specified motion model. So based on a motion model of how a vehicle actually moves, as well as the propagated sensor data, which we basically integrate over time to give us a better estimate, we basically are able to create a real-time scan of our environment. And after that, the particles are assigned weights based on the likelihood of receiving the rain sensor data. So this is basically like it basically helps to remove outliers because sometimes we get random scans in our data, and this can lead to like a wrong estimate of our position. So by assigning weights, we help to eliminate potential outliers and get a more accurate position in our sensor environment. And finally, third part is basically resampling and reevaluating the particles repeat iteratively until the particles with the lower weights are eliminated, as these are most likely not going to be in our vehicle's position. So once this is done, the MCL system object basically outputs the estimated pose and covariance, and the estimated state is basically the mean and covariance of the highest weighted cluster of particles. That means basically the region where the particles are most concentrated and when they have the highest weight. The output, and this is basically given in terms of our GPS coordinates, and as well, and this also gives us and by using the sensor data, we can also get the idea of where our objects are related with respect to this position. And so the process basically involves repeating all these steps continuously of resampling our sensor data and evaluating the particles likelihood again and again until we eventually reach a point where we're able to track it efficiently in real time. And that's basically localization. And the last slide is basically the references we've used for discussing all of this. And I've listed all the different references I've used, and also added particular parts like where you can read about RCNN, KLT, ACF, and RANSAC. And that's basically all for this section. Thank you.
My name is Andrew, and I will be presenting the last two parts of the project, the first being the state flow decision making. This is an overview of the state flow. As you can see, there is a total of 3 main separate blocks. These blocks receive a series of high and low signals that act as the logic for switching between the different states. The 3 main blocks can be seen in the top left, top right, and bottom center. All 3 are connected to a central state, which is the emergency state, which I will talk about later. This state flow was designed in reference to the path as seen in page 4, which was an overview of the Easton Town Center. The first state flow is the shuttle stop state flow. This state flow is accessed whenever a stop is needed by the shuttle. There are a total of 5 states, 3 signals to transition between these states, 2 output signals, and 1 input signal. The first state is for the shuttle to come to a stop. It then receives a doors equals 0, in which case all doors are opened. It then receives a passengers equals 1 signal, where it tells the shuttle that passengers will be loading and unloading. The door signal then sends a high bit of 1, which tells the shuttle to close all the doors, and then the start signal sends a high bit of 1, telling the shuttle to begin its normal route. One of the output signals you can see below is the route equals 1 signal. This signal tells the shuttle to continue its normal driving operations. The other output signal is the emergency signal. This signal sends a high bit. The shuttle stops immediately and performs an emergency protocol. The input signal to this block can be seen at the bottom left. If a stop equals 1 signal, it tells the shuttle that a stop is approaching and this state flow is entered. The second state flow is the intersection state flow. This state flow consists of 5 states, 2 signals to transition between these states, 2 output signals, and 1 input signal. This state flow is accessed by the input signal intersection equals 1 found at the bottom center. If this signal is sent, the shuttle knows that an intersection is approaching, and it will do the following. First, it will establish if it is the lead vehicle in the first state. If it is not the lead vehicle, the lead signal will send a 0, and it will follow the vehicle in front of it. If it is the lead vehicle, the lead signal will pass a 1, in which case it will tell the shuttle to examine the traffic light. If the traffic light is green, the green signal will pass a 1, and the shuttle will continue its normal route. If the green passes a 0 bit in that signal, the shuttle will slow down and stop and wait for a green light. Once a green light is detected, the green signal will pass a 1, and the shuttle will continue its normal driving route. As you can see, one of the outputs, again, is the route equals 1 signal. This signal will return the shuttle to normal driving operations. As you can also see, there is an emergency signal, and if the emergency signal passes a 1, the shuttle will enter the emergency block and stop the shuttle immediately.
Hey guys, it's Kevin, and I'll be talking about some of the conclusions we've drawn from our project. So in this project, what we've basically done is that we've designed an autonomous shuttle vehicle to replace the Easton Town trolley for low-speed operation. And the vehicle was chosen such that it can accommodate about 6 to 12 passengers, and we basically calibrated its latitudinal and longitudinal dynamic parameters accordingly. And the vehicle uses a drive-by-wire system, and the actuators are basically controlled via CAN. And drive-by-wire is basically a mode of electronic control. And some of the sensors involved were it uses LiDAR, camera, and radar for perception, and it uses GPS and IMUs for the localization purpose, which we've talked about before. And we do this basically using the MATLAB's Automated Systems Toolbox, which uses algorithms like KLT, RANSAC, Monte Carlo to analyze and extract the information required from our sensor data. And so for the longitudinal control aspect of our vehicle, we basically modified our previous model of our previous longitudinal model, and to include wind velocity as basically the area in which the shuttle will be operating is severely affected by wind, and also due to the flat nature of the road in the area, we basically taken our alpha value to be 0, and we've simulated it accordingly. And we observed that the vehicle was able to gradually accelerate to a steady state speed just below the limit, and how it also managed to decelerate from that steady state to 0 in a short span of time. And for the lateral control design, we observed that our vehicle has an inherent understeer characteristic, and we also observed how both the linear and non-linear models satisfied our performance requirements at low speed, and we chose to proceed with the linear model due to its relative simplicity. And for our path following, what we did was we modified the state space model and approximated our path to be smooth for simpler computation purposes. And once we changed our PID values and simulated, we noticed that while initially, from our path error and the error vector, well, that while initially the error was really small, over time during the middle part and towards the end of our path, we noticed how the effect of the accumulated error. And we basically concluded that if we were to use a more robust control instead of the traditional PID controller, that this issue could be resolved. And for collision avoidance, we use the ABS implementation as it suited better our project statement. And what we did was we used pedestrians as obstacles with 0 meter per second velocity, and the vehicle transfer function and speed limit were also modified according to our requirements. And what we observed is that while the shuttle took a few seconds to decelerate to 0, it was able to decelerate from 15 to less than 2 meters per second almost instantly, which is the ideal response for a vehicle. And based on our path, a state decision chart was made, which basically took into account 3 different scenarios, namely how the vehicle behaves during shuttle stops, the basic shuttle route, and as well as during signal intersections. Finally, at the end of all this, we prepared a list of real-world challenges which our models do not take into account for because we assumed ideal conditions, and we basically mentioned and calculated the risk factor to our shuttle's operation, and we've noticed that the factor which had the most risk was the case when pedestrians do not use the crosswalk, as the vehicle may not be able to detect this, as it is again designed according to ideal conditions. So that's all. That's basically it for our project, and we hope you enjoyed this presentation. Thank you.